This is Climate Watch. I'm Zhao Ying. Welcome to the show. You may still remember the Hollywood blockbuster The Day After Tomorrow, where a sudden collapse of the ocean's currents plunges the world into an ice age. While the movie dramatically exaggerated the speed and scale of those changes, the ocean circulation system at the center of the story, known as the Atlantic Meridional Overturning Circulation, or AMOC, is very real. It acts like the planet's vital climate conveyor belt, moving immense heat from the tropics up to the northern hemisphere. But as the planet warms, growing evidence suggests this critical Atlantic current is weakening. A recent study published in Science Advances warns that AMOC is on course to slow by more than 50% by the end of the century, potentially leading to an eventual collapse. This follows research showing that AMOC has already been weakening at 4 different locations in the Atlantic over the past 20 years. So how worried should we be? What would a major slowdown of AMOC mean for our climate? And how close are we to a potential tipping point? Joining us now is Paul Beckwith. He is a climate system scientist based in Ottawa and a popular content creator on YouTube. Paul, it's great to have you with us.
Well, thank you for having me.
So first of all, can you explain in simple terms what AMOC actually is and how it impacts our planet's climate system?
Yes, so AMOC, the Atlantic Meridional Overturning Circulation, it basically describes the movement of the ocean currents in the Atlantic, mostly in the north-south direction, which is what Meridional is looking at. And then, so you have think of the Gulf Stream off the U.S. moving northeast across the Atlantic. So it's warm, it's salty. As it goes further northward to higher latitudes, the water cools down. And so you have colder, salty water, which is very dense. So that water sinks at certain points up in the far north, and then it goes down and comprises the deep water, which then moves its way back southward. So the AMOC is part of what is more generally called the thermohaline circulation, the THC, or the entire ocean circulation system, which is driven by temperature and salt content, basically. So it's a way that the oceans transport heat and salt. And, the Earth tries to, the poles are very cold because of the geometry of the sun on the Earth, etc. The poles are very cold. So the ocean currents try to bring heat from the temperate regions near the equator to the polar regions to try to balance things out a bit. So it's a very, very key component of the climate system. For example, the heat carried northeast across the Atlantic Ocean is very important for providing heat to northern Europe. Areas of high latitude in Europe are much warmer now than they would be if the AMOC didn't exist. So it's very important for global, for a whole climate system, essentially. And there's a very landmark paper in 1991 by the famous U.S. climatologist Wally Broecker. And the paper is called The Great Ocean Conveyor. So he described it clearly then. One of the leading experts on the AMOC is Stefan Ramsdorf at the Potsdam Institute. He's been studying the AMOC for 35 years.
Yes. Tell us more about the main physical factors that control or destabilize this circulation system.
Yes. So the main controls are the temperature, because warm water has a lower density. It's not as heavy, so it tends to float on the surface versus colder water, which is denser and sinks below. And salinity is also a key factor in the density. So saltier water is heavier, more dense versus fresher water. So the main controls are the temperature and the salinity, thus the thermo for temperature, haline for salt content. The Gulf Stream, there's also a lot of factors, like it's a wind-driven current essentially as well. So changes in the freshwater inputs in the far north are the reason for the AMOC weakening. So we're getting lots of melt from Greenland, and that fresh water enters that region and makes it fresher. We're getting, because the water is warming from climate change, it's a lot lighter and it's got less tendency to sink down to form the deep water. And also, as we get more rainfall patterns change, that freshens the water. We're getting more rainfall in the far northern regions. And so all of these factors, we're getting more river runoff from high Arctic regions. So more and more fresh water makes the water lighter and less likely to sink down, and then that slows the AMOC. And there's a very strong reinforcing feedback because as the AMOC slows down, there's less transport of that salty, warm water to the north, so it becomes fresher and fresher, and then the whole system can basically slow down severely or even shut down, which would basically be really have really detrimental effects to people. The climate system would completely refigure and change if that was to occur.
Okay, so human activity does have a huge impact on this system.
Yes, human activity has a big impact because we're definitely warming. We're getting lots of warming of ocean water at the surface. We're getting lots of so-called marine heat waves that we never had before. And part of that is to do with fewer low-level clouds over the ocean because there's less sulfur in the shipping fuels, and the sulfur, those particles act as cloud condensation nuclei, generating low-level clouds. We're having fewer clouds. So the actual albedo or reflectance over the oceans and over the whole planet, in fact, has declined significantly. So the Earth radiation imbalance is increasing, and we're getting that more warming. We're also getting more precipitation in the form of rain further north as we get this polar amplification. The Arctic region's warming 4, 5, 6 times faster than the rest of the planet, depending on what latitude you're at. So all of these things are combining to stratify the ocean more. It's more layered. You get a warm freshwater cap on top of colder water, so it reduces vertical mixing in the ocean, which is very bad because the ocean is a huge sink for carbon. The oceans absorb about 26% of human emissions every year, and those numbers can be reduced with stratification. And of course, all of these things are bad for the overturning circulation system.
Yes, so now scientists have warned that with enough warming, the AMOC could weaken dramatically or even collapse. And that often brings to mind the day after tomorrow, where the world freezes over in a matter of days. But how accurate is that Hollywood scenario, scientifically speaking?
Yes, I actually loved that movie when it came out. I watched it multiple times. The premise of the movie is that the AMOC collapses, and that's a very real possibility. But of course, the movie, to capture audiences and be a Hollywood blockbuster, things have to happen, very quickly. So the biggest error in the movie is the time scales. An AMOC shutdown, it wouldn't happen overnight or in a few days. It would take, months, to years to fully play out. And also in the movie, there were some of these superstorms and freezing events that happened almost instantaneously. And that's not real, that's not how the weather system works. But, the movie does get across some very important concepts about the idea that the AMOC can actually collapse and it would change society significantly. So that part is true, but the details are, done for Hollywood purposes.
Okay, so I understand this is a more gradual process, but if the AMOC were to undergo a major weakening or even a collapse, what could the consequences look like for the global climate system?
Yes. So this is the key question. So first of all, the time even an AMOC collapse that played out over months to years, that's a very small time in the whole scheme of paleoclimate and human existence on the planet. So, it's not going to be happening in a couple of days, but the consequences are extremely severe. So. Basically, you can think of a total reorganization of the climate. So some of the things that we think would happen with a shutdown, the northern hemisphere, above 60 degrees north, would experience temperatures up to 7 degrees Celsius colder than they are now, especially in wintertime. So many places, Europe would go into a deep freeze in winters, and it would also be a lot cooler in summers. The southern hemisphere would going south of 60 degrees south to Antarctica, the temperatures there would warm on average about 6 degrees Celsius, which, because there'd be much less heat going into the northern hemisphere, it has to go somewhere. It wouldn't stay at the equator, it would go into the southern hemisphere. As a result, the tropical rain belts, which are often known as the ITCZ, Intertropical Convergence Zone. That band of rain near the equator would shift to the south. Think of that band as basically at the midpoint. The heat northward of it and the heat southward of it is kind of balanced. So if you're putting a lot less heat to the north and there's a lot more to the south, the whole band would shift southward. So the regions that rely on that rainfall for crop growing, etc., would be out of luck as that rainfall belt shifted southward. The jet streams would completely reconfigure. If the ocean current system's completely refigured, which is reconfigured, which is what we're talking about. So I often talk about weather wilding, weather whiplashing, weather weirding. The whiplashing going from one state to another state rapidly, and the extreme weather effects around the planet would just greatly accelerate. And one of the biggest factors that would affect humanity is our ability to grow food. Because if you think about the major crop growing regions around the planet, they rely on a certain climate, a certain rainfall and heat temperature regime throughout the year, for planting and harvesting, etc. But if those optimal climate conditions shifted somewhere else, we can't suddenly start growing food to where they've shifted because the soils haven't developed in those regions. So we're basically, if the AMOC shut off, we're looking at global famine for sure. We're looking at global food shortages. We're looking at difficulty for people to get proper water and everything else. So this is there'd be societal chaos. People often talk about collapse of civilization and stuff. But I think, when people in the West talk about collapse of civilization, I think that for the most part they exclude China because they don't understand China, right? China to many people in the West is just like a black hole or something, and there's propaganda that's very, anti-China in many places, and people just don't understand. I mean, I try to argue that China's doing more to try to address climate change than all the other countries in the world combined by the clean energy, the solar, the wind, the batteries, and all this technology. So basically, I think places need to start preparing and thinking about what will happen if the AMOC will collapse, because the risk is extremely high that it's going to collapse a lot earlier than people can imagine, even or even know about, or even aware
Yes,
of.
yes, that is true. And the whole planet will feel the impact. But Iceland has actually designated a potential AMOC collapse as a national security concern. So, does the North Atlantic region face a more direct and more severe threat compared to the rest of the world?
I think Iceland is very smart to do this. They have a lot of, and they're extremely worried about it because they're in basically the bullseye of an AMOC collapse, right? They're right there. If the AMOC shuts off, they have immediate direct effects, as does actually the United Kingdom, Ireland, Scandinavian countries, Greenland, parts of the coastal North America as well through greatly increased sea level rise. Because if the Gulf Stream changes, stops going northeast, bringing all that heat, well, that hot water gets pushed up closer against the coastlines of the U.S. and we can get over a meter sea level very quickly, there with an AMOC collapse. It's so we talk about the direct effects are hitting those countries I've mentioned, but of course the globe faces the second order, third order effects, like the global threats to food supply, et cetera, are huge, right? But these aren't direct effects; these are more secondary or tertiary effects of an AMOC collapse. I mean, nobody gets away scot-free. But the UK, for example, with an AMOC collapse, the sea ice in the winter would probably extend from the Arctic right down to northern parts of the UK. So
Yeah.
everybody is going to be affected.
Okay. And this weakening can be irreversible, right? Because some studies suggest that once the AMOC weakens past a certain point, it may not recover for centuries, even if warming were reversed. So why is there such a tipping point?
Yeah, so it's a highly nonlinear system. So it exhibits threshold behavior. So if you're okay and then you cross a tipping point or threshold, I like to talk to people. I like to tell people, start leaning back on your chair and then take the force off and you correct. But if you lean back to a certain point, right, the tipping point of your chair, it's either you fall off backwards off your chair or you go back to sitting on the chair, in a stable configuration. And if you fall off your chair, you can't just move the chair up with yourself, right? You have to get off and straighten the chair. Like the when you're going in one direction in this process, you can't reverse the direction. Like same thing if you're in a canoe and you're tipping it. A lot. I'm in Canada. Let me talk about canoes, right? If you're tipping a canoe, you can correct, and then you reach a certain point where it's very unstable. And then you can either tip the canoe and end up in the water, or you can correct back. But when you get near that tipping point, there is something called a critical slowing down. So the system loses its resilience and becomes kind of rigid. So basically, it's like hysteresis. Many engineers talk about hysteresis in materials depending on the magnetic and electric fields. And if you go one way, if you increase a current, you can tip and then you can't come back. So basically, the path that you follow, if you tip and you suddenly take the forces off and try to go back and restore where you had, you're actually in a different state. So these systems like the AMOC, they have bistability or even multi-stability. So bistability would just be an on state, which is the existing state of the AMOC, and then an off state where it's no longer off. And then there's some models and people argue it's multi-stable. You can have like a state where it's weak or it's somewhere in between the two. And that, but basically these systems, and if you go, the ocean, it takes a lot of time for heat to move in the ocean and for fresh water to move in the ocean. So fresh water is accumulating in huge amounts in the far north, and the water's warm, the AMOC tips off to an off state. It takes a long time for that fresh water to spread and dissipate and become salty again. It takes a long time for the heat to leave. So the AMOC would basically be off for hundreds of years, perhaps even 1,000 years. We know this from behavior of the AMOC shutting off in the paleo records, something called Dansgaard-Oshur oscillations and Heinrich events as we were leaving the last ice age. So we've seen this behavior from records, sediment records and isotope records. We know that it's happened in the past, and it looks like we're heading to that sort of thing again, unfortunately.
Okay, but I think we've only had continuous monitoring of this AMOC since 2004, right? So is 20 years of data enough to distinguish a permanent weakening from the natural multi-decadal variability?
Not by itself, because, is it a permanent weakening because of forces, or is it natural multi-decadal variability, right? 20 years isn't enough. I mean, the data is actually, we have moored instruments in the ocean at various latitudes to measure the water flow past them. Those are direct moored arrays. The most important one is probably the 26-degree north, so-called rapid array. And you can measure 17 spherdrups of flow. Spherdrup is a million cubic meters a second of water flow, massive volume flow rates. You can measure the heat, 1.2 petawatts of heat. A petawatt's 10 to the 15 watts. So we've got that data, and those moored arrays only went in 2004. We can go back about 5 years before then to something called the Argo floats, which are floats they're autonomous floats that around the ocean. There's about 4,000 of them now. They move with the ocean currents. They measure temperature and salinity. But again, so this is direct instrumentation measurements. But we have a lot of indirect measurements as well. We have paleo data. Okay, so we have paleo data, which is data from sediments and oxygen isotopes, and they show that the AMOC is the weakest that it's been in 1,600 years. We also have models and ensembles of models where you force the system or you take the forcing off. So that tells us a lot of information. We also have indirect proxies. Other methods of indirect measurement, like for example, sea level rise data off the east coast of North America, because when the AMOC changes, we know how that will affect sea level. We have a lot of data from ice cores in the in Greenland. We also have data from the ice cores in Antarctica that, the Greenland cores go back to the last warm period. They're good for but the stuff the ice cores in Antarctica go back 800,000 years more. Some of them even to 1.2 million years, whereas Greenland's, the last 100,000 years or so. So we can combine all of this data and we can actually figure out what's happened before. The newer technologies are allowing us to get really good, accurate data, but it's not that we didn't have any data before, it's just from multiple sources, but it's painting a picture of the AMOC, and that picture is becoming clearer as we get more and more observational data.
Yeah, and also in terms of the future trends, the scientists are using climate models to project the future, but those projections can vary widely. So, why is it so difficult to pin down in our simulations? And based on the evidence we already have, is there any emerging consensus on just how close we are to its collapse?
Yeah, so the models, in general, so there's a recent paper I think we can talk about, in a minute, that just came out that's talking about it's actually model and observations, and it has very dire news compared to the rest of the models. But the rest of the models, basically, there's a lot of variability because the AMOC's a density-driven process, and the density of the water, of course, it depends on the temperatures, the mixing of the water, so temperatures through the water column. It depends on the salt at the surface and salt through the water column. And when we get, if we get more ice melt off Greenland and it's fresher water, and if we get more rainfall in that region, it's fresher water. If we get more river runoff, it's all fresher water, which makes the water lighter and less likely to sink down to the abyss. But then, when you get sea ice formation, about half of the salt is trapped in the ice, and it eventually trickles out of the ice in through brine pockets in the ice over 4 or 5 years. But basically, when the ice is formed, that uses, a lot of the salt is rejected. Half of the salt is rejected and stays in the water that doesn't freeze under the ice. So that increases the saltiness, the salinity of that water, making it heavier, more likely to descend down. So what I'm saying is there's lots of different parameters the models are trying to look at. The grid size of the models is different. The complexity of the models is different. The run times of the models, they're starting to incorporate more and more AI. So they are getting better over time. But there is a lot of variability in the models.
Yeah, and some recent studies are suggesting that it may actually collapse earlier than we thought. And I think just now you mentioned the recent study. I believe you were referring to this study in Science Advances that suggests the AMOC could slow by more than 50% by the end of the century. And that is significantly more than many climate models had previously projected. So can you walk us through its key findings?
Yeah, so the key thing about this model is it uses the latest physics that we know, like from the on oceanography and behavior of the water and how the density is changing. It's it incorporates a lot more observations than the previous models, and yeah, I mean, it's arguing the probability of an AMOC collapse by 2100 is 51% with an 8% variability. So it could be almost 60% or, 43% or so. The models, when you have a collection of models and an ensemble of models, there are some models that are much more pessimistic than other models, and it turns out that the more pessimistic models in those ensembles are being more and more. It's becoming there's more and more likely they're more and more likely to be accurate models of what's really happening. So this latest model it's just more sophisticated in terms of the grid size and the computing power behind it and the incorporation of observations. And they're using some new techniques, something called ridge regression, on to weigh the different models in the ensemble. And there's something called CMIP6 models, which stands for Climate Model Intercomparison Project, the sixth version. So it's the most sophisticated models, and the data will go into the next sort of intergovernmental panel on climate change reports, et cetera. So Stefan Ramsdorf, I mentioned him as being one of the world lead. He's one of the most knowledgeable scientists on AMOC. He's been looking at it for 35 years, he's extremely worried with these new results.
Are there any observable warning signs that can indicate whether the AMOC is approaching a collapse or a tipping point?
Yes, there are many. So first thing to mention, remind people, the AMOC is the weakest in 1600 years. Okay, so this is from the paleo data, and we know how it behaved coming out of the last ice age with these so-called Dansgaard-Oshur oscillations and Heinrich events, where the AMOC shut off and restarted, hundreds of years or 1,000 years later after it shut off. There's one of the most significant worrying factors is there's been a decline in the observed freshwater transport at 34 degrees south in the South Atlantic. So the South Atlantic salinity has been increasing. So there's when it crosses the equator and comes up northward into the North Atlantic, the water is there's less the characteristics of the water flow are different than they were before, and this is thought to precede an AMOC collapse by 1 to 2 decades. This is very recent research from 2026, also 2024. There's also a cold blob in the North Atlantic south of Greenland. So if the Gulf Stream actually changes position and doesn't go through this region south of Greenland, then the temperature anomaly will be negative. So it'll be a cold blob or a global warming hole, some people have called it. And that's an indication of the changing nature of the Gulf Stream, which is the AMOC, which is a big part of the thermohaline circulation. There's The Gulf Stream is also being noticed to be changing its position of flow off, for example, on Cape Hatteras in the the Outer Banks of North Carolina. The Gulf Stream runs fairly close to the coastline, and the nature of it has been changing. It's in a different position. It's shifted position, which is something we would expect with an AMOC collapse. I've mentioned, if the Gulf Stream is carrying water, not where it's presently going now, but if it's carrying less water northeast towards Europe, then there's more water from the Gulf Stream piling up along the U.S. coast, which would greatly warm the water off the U.S. coast and could increase sea level by up to a meter if the AMOC shuts off. But we're seeing huge rise in sea level off that particular region. And also the statistics, you can look at the statistics of the AMOC flow rates, and they're starting to be more variable. There's more excursions higher and lower. And also there's something called the critical slowing down, which the response time or recovery rate when it deviates from the stable, the norm, if you like, is taking longer. And it's something in math known as autocorrelation lag -1. And this is meaning that this is showing when you have, I mentioned the canoe tipping, I mentioned the chair tipping. When you get to those tipping points, the system loses flexibility, the recovery rate decreases, and the variability or excursions increase. So all these things are showing that the AMOC is slowing down. So when you combine all this evidence, it creates a pretty clear picture, I think.
So even with uncertainty about timing, does the risk level alone justify stronger policy action? And what exactly can be done?
Yeah, yeah. I mean, there's only one answer to one honest answer to that question. I mean, risk is the probability of occurrence times the consequences. So it's looking like the probability of occurrence is increasing. The risk, the overall probability could still be quite small any given year, but it's increasing due to many factors. But the consequences I've described, the consequences are, for example, human ability to grow food to feed everybody on the planet, right? I mean, an average temperature rise of +6 degrees in the southern hemisphere and -7 degree temperature drop Celsius in the northern hemisphere. Everything's shifting, rainfall patterns, jet streams. We're living on a different world essentially. So, how are we gonna, when climate shifts and we can no longer grow food where the soils are, what do we do, right? So anyway, the consequences are enormous, right? The consequences are, huge for society, for humans and society on this planet. So when you multiply a small number by a huge number, the risk, that gives you the risk. So the risk is really high.
Yeah, and I know some scientists are even exploring some more radical geoengineering ideas, like a proposal to dam the Bering Strait between Alaska and Russia. I mean, can you explain the logic behind this?
Yeah, I mean this of course, is I would say is absolute nonsense. I mean, I love bold, ideas, but this idea, I mean, the idea is that the salinity in the North Atlantic is about 36 PSU. PSU, practical salinity units, it's weird. It's like it's parts per thousand really. So to convert 36 parts per thousand to 36, it's 3.6%. Parts per hundred is percentage. In the Pacific, it's slightly less salty. It's 34 PSU in the Pacific versus 36 in the Atlantic. So the idea is that some of the Pacific water going through the Bering Strait and then eventually into the Atlantic brings some fresh water there, which can increase the probability of an AMOC shutoff, right, with the fresh water. So if you prevent that fresh water getting into the Arctic and crossing, but I mean it's a ridiculous idea, really. I mean, sure, bold ideas are needed. I mean, I let me throw out a couple equally ridiculous bold ideas, okay, just for fun. Okay, what we could nuke the deserts. That would kick up dust into the atmosphere, block some sunlight, and cool the planet.
Mm.
We could blow the top off of an active volcano and cause it to erupt. And when a volcano erupts, it puts sulfur dioxide into the stratosphere, and that cools the planet up to a degree or 2 degrees even for 3 to 5 years. Right? So those sort of things to cool the planet, that happens, whenever a large volcano goes off that puts sulfur dioxide in the stratosphere, we get a cooling. So those things, are those any more ridiculous than, building a dam across the Bering Strait? I don't think so. The thing that I think would really work is trying to increase the sink of the ocean for carbon. Sprinkle iron dust in the ocean, cause phytoplankton blooms, and absorb huge amounts of carbon. But then you have to deal with ocean acidification. Anyway, there's people can throw out lots of different ideas, and people are getting desperate. So some of the ideas are getting more and more, crazy sounding, right?
Okay, so you doesn't believe in any of these geoengineering ideas,
Well,
whether it's solar.
well, no, so what can we do, right? That's the big question. If the AMOC's going to shut off, and once it does, we're stuck in that state. I've been talking for years about the three-legged bar stool, is what I call it. Okay, leg one is to slash fossil fuels, but we're not seeing that happen at all. Leg two is carbon dioxide removal and methane removal from the atmosphere. And I'm not talking about net zero, because we're at 431 parts per million. Net zero, if we zeroed our emissions, we would just stabilize at very high CO2 levels in the atmosphere, and that's too high. We're still going to have all this extreme weather and problems, and we could still get an AMOC shutoff. So what I'm talking about is, our human emissions are about 30 gigatons of CO2 per year. What we really need to do is draw down the CO2 levels back to something like 350 or 300, which we know lead to a stable climate. And I think the most promising way to do this is to try to increase the amount of CO2 that the ocean absorbs. So we need to understand where, and a slowing AMOC was going to reduce the amount of carbon captured by the ocean. But there are, I've mentioned the Gulf Stream a lot. Spinning off, when you have water moving on the surface very fast, it draws water at the side towards it, and you create eddies that are counterclockwise and clockwise. Small, they're on the order of 100 kilometers or so in size. The eddies that move clockwise in the northern hemisphere, if you take your fingers, the right-hand rule, move your fingers in a circle, your thumb points downward. That's a clockwise eddy in the northern hemisphere. There's something called Ekman flow, which moves water downwards. So if we created phytoplankton blooms in those eddies, then that carbon, organic carbon, would be drawn downwards. And so there's a lot of work from eddies in the ocean. We don't understand enough about it, but I want to draw your attention to this paper in Science Advances. It's by all these Chinese academics. It's called Oceanic Uptake of CO2 Enhanced by Mesoscale Eddies, and I think it's a very key and important paper. I think that we have huge potential, I believe, for drawing down vast amounts of CO2 in the eddies of the oceans around the world. So we need to look at that carefully. So that gave me a lot of hope when I was learning more about it recently.
Yes, Paul Beckwith, thank you so much for joining us today.
Well, thank you for having me.
And that wraps up this edition of Climate Watch. You can find more episodes on your favorite podcast platforms. Just search for Climate Watch and hit subscribe. Don't forget to leave us a quick review or share it with a friend. You can also email us at radio@cgtn.com with your questions or feedback. And stay updated on the latest climate stories with our Substack newsletter, Climate Choices. I'm Zhao Ying. Thank you so much for listening. See you next time.